because it's perfectly fine to answer questions. I won't be able to, but I'll at least stand up in front of you and show you that I too don't know. So, simplicial sets, right? They're kind of a weird old thing. I wouldn't say that the natural thing to do is to think of a simplex as a category, but what's the purpose of doing that kind of nonsense?
Generalize it, then bring it back down.
Generalize it to what? So, I mean, why do we have the simplicial set model? I'm going to talk about other things in a second, but I think it's okay for us to. So is this too abstract, or does this have a point? I mean, we can generalize anything, right? You know, study of frogs might be categorical if you want it to be. But what do you get for that?
So I remember, last time said it was like, you can study discrete spaces in topology now, where the discrete things are categories.
Right. So the storyline, the growth index storyline. Maybe that's spelled in the same alphabet, somewhere around there. Okay, so growth index story is that infinity groupoids and things like it might be spaces where you relax the meaning of space until it matches whatever the relaxed meaning of infinity groupoid is. Like both of them are moving targets. If you relax them both, then they become the same thing. And maybe this will inspire you to study it a different way. Okay? But again, if I was talking to my biologist colleague, should they get excited by this? Is this just, topology doing more topology, or is this like something we can take outside? I mean, if we don't ask these questions, we end up just talking to ourselves, right? We just end up siloed, we end up becoming irrelevant. So let's do our best to try to make some of this stuff a little bit more motivated so you can talk a little bit more interested to colleagues outside. So one of the things that I think we're going to do today is try to investigate this side of the storyline. How do groupoids show up as things that you do actually ask and study? And then what I want you to think about for space is just the toolbox we have here. I mean, the reason to build something into what we call a space, if it's close enough to what we think of as a topology, the toolbox is huge. And we have so many things we can do. We can prove things have like a unique number associated to them. Like I tell my students that one of the most powerful things about vector space is the concept of dimension. That it doesn't change, It's just, that's a number you can be counting on. And you can then use it to describe rank. And then you can do that to predict whether you found all the solutions to a system of linear equations. Like it triggers a lot of things. So you want to come from a place that has a lot of tools. But that's not good enough. You want to go to a place that has a lot of questions. Okay? So that's my goal today, is to discuss this with us all so that we have some hopes of like thinking about these things. The simplicial sets thing, let me go ahead and demystify why I don't think it's too abstract. It's rather just necessary. I don't think these are the questions to ask at all. The point is, if you're going to go with the category approach to things, then you're going to have to turn the other things into categories. Like this, the reason to have to make simplices, which you know how to draw as like a triangle or a tetrahedron or something, if you're going to make this talk to other categories, then you have to make it into a category. So the simplicial set idea is to say, what is the category version of simplices? You'd be forced into that. So then you back the question up to why are we even using categories? Why is that the description we want? And I have one answer for that. This is James' answer, not a worldview answer. This is just me trying to help you see where it's at. Categories have one, few operations. Two, map onto known structures. And then most importantly, our recursive theory. So that's what I'm going to try to demystify and then get into the infinity groupoid or just groupoids and then infinityize them as we go. So a few operations. We sometimes start people out with categories being like the galaxy of all things of some kind and then the morphisms between them or whatever. But that's a little bit kind of, that's one story. It's a very small piece of what's really going on. What you really have is you have some type of data. This might be concrete types in the sense of type theory. It might be an informal type in your mind. I don't really care to specify at the moment. You have an operation. And okay, it fails sometimes. You can't always multiply everything in there. So I'll put a dotted in here to mean it's a partial operation, meaning not everything in the domain is actually in the domain. Just like your good old classic pre-calculus class had 1 over x be a function, and then you divide later that, well, we don't divide by 0. Okay? And then you have some properties such as it's associative when defined. And you know when it's defined. Unary? Unary? Is that how one spells unary? Let's go with it for today. You have unary operations that specify when multiplication is defined. So it's just a type of algebra. I didn't write down the associative law, and I didn't write down the extra conditions here, but this is all that it is at the end of the day. That's easy to start to try to satisfy. You just have to come up with this, and this one we end up calling what? What's the name for that thing? Does anybody see? I mean, I've really hidden categories completely from sight on purpose, but let's try to recover it.
Those would be morphisms?
Yeah, these are the arrows. A for arrows. And so what do I do with arrows? I compose them. Composition is meant to be associative. I'm allowed to define the product when I have some notion of a domain and some notion of a codomain. So the two hidden unary operators, as soon as I write them, you go, oh, of course. One unary operator is called the domain of this arrow, and the other one is the codomain of the arrow. And you have to match those up to be allowed to use. So that in some sense, and by the way, you might say, well, wait a minute, that can't be an operator because the domain is a set of some kind or some object, and f is an arrow. Well, I'll fix that for you by saying you would think of this as the identity on the domain. Okay, so if f was from A to B, then you don't ever actually have any objects at all. You just have the identity functions on those, and that plays the role of having the objects. So there's a whole lot of people who study categories this way. And this gets to my earlier point. Few operations. The fewer things you have to then go define in your sciences, the better. You'll match this to a lot more objects. All right. Maps onto known structures. Well, once I tell you the relations between data sets, these can be functions, these can be less than or equal to signs. There's a lot of data that gets related in a binary fashion, so that's reasonable to map onto things. What about this recursive part? It's the last critical ingredient to making these a powerful theory builder, like the good foundations for building a theory. What could I mean by recursive?
Get string together composition?
That's true, I can string together, but I can also string together, say, Lie products, and we don't make those into categories.
Like self-referential?
Self-referential in what sense?
You can say A's, like a composition operator, say.
I think that's similar to what Colin was suggesting of the composition being recursive, and that's certainly the case. This is a homogeneous product instead of a heterogeneous product, so just for your own minds, you think of like a vector space product, right? A distributed product on this is heterogeneous algebra. And that's much harder than homogeneous algebra. Right, over here you have homomorphisms, meaning it's one function because they're all one set. Over here you need heteromorphisms, you need to be able to transform each of these independently. So the whole algebra gets more complicated. But that's not quite the recursion I'm after. But the recursion I'm after, of course, I'm fair to tell you something and then expect you to guess, but it's worth your brain power to think about it, I think. The recursion I think is important is that the category of all categories is category. Okay? The idea is that this theory can zoom in and zoom out. Once you want to try to combine things together, this isn't true of a lot of structures, right? The class of all vector spaces is not a vector space. All right? If you take endomorphisms of a ring, those of you who are algebraists, but endomorphisms of a ring, I mean the homomorphisms from phi from R to R, and these preserve addition, and they preserve multiplication, right? What kind of an algebra do I get out of this endomorphism?
Ring.
Is it a ring? It's a good guess. Is this a ring again? There's some head shaking yes, and obviously I haven't said yes, so somebody should disagree with you.
Should be agree because we just have composition of endomorphism.
So we have composition, right? So composition is some kind of what type of operation?
Binary operation.
Sure, it's binary, but like what's an identity it has? Is it commutative? Is it associative? Does it have inverses?
Associated.
It's an associative. So composition is associative. So we're halfway to something here, or not even halfway. We're like we're on the board with an operation that's associative. But if you think this is a ring, you need to come up with another one, right? Go ahead.
Just mapping, we don't have a zero.
What about R goes to 0? Okay, you could be saying that maybe I want 1 to go to 1, right?
Oh, yeah.
Okay, well, I'm willing to relax the unit here, if that would fix it. I claim it doesn't, so the answer is this isn't a ring, okay? But even with the 1 going to 0, but if that was already a rule that 1 must go to 1, then you would already have a failure of 0. That would be an indication. But that's not enough, because I just relaxed 1, and I still found a problem. What's the other operation you'd want to put on these things?
Adam.
You want to be able to add things, right? And if you add things,
Oh. That's annoying.
and you want this to actually be something, let's just see that it's a homomorphism under addition. I don't know if this is the one I want to check or not, but I'm just checking one of the things. So that's one of the things it could be. I think I want to check composition, actually. That's probably their product. I just had to think through what would fail. There we go. Okay? And if this was going to be a ring homomorphism, what would I want this to actually be? This is the goal, would be that this should just be phi of AB, phi plus t plus tau of A times phi plus tau of B, right? And what's going to happen is if you expand this out, you have different numbers of terms, and there's no obvious cancellation. So this theory is not recursive in the sense that you can't study rings with just rings. Just even to study the homomorphisms from the ring to itself leaves ring theory. And so this is a non-recursive theory. You have to leave the theory to study the theory. Okay? So places that mathematicians have gravitated towards historically are places where the theory can study itself. Because then you can sort of build some basic atoms and start to build them up by building out their consequences. And recursively you build out some big implications from some small ideas. Some small identities can then be responsible for bigger ideas. And categories have that feature. that if you start looking at the category of categories or things recursively, you actually land back where you were. Now they get bigger, right? Like endomorphisms are more than just R, right? This got bigger. So things do, you meet new problems, but you meet them with the same theory you've already been cooking up. So your theorems start to build and they become powerful in that way. Because that's one of the main reasons that people gravitate towards this mathematically. The other one is, well, there's a lot of things that are actually like this, things that are functions. Okay. All right, so I'm going to try to point out why this gets hard. I want to go to this question mark here.
Do you want me to do that?
Yeah, sure, sure. If you would like to, you can steer away. For some of our viewers out there who want to tell us what we're doing wrong.
For thousands of years.
Well, it could have just been me sitting there hitting replay all winter break. Okay. Let's start with this straightforward question. How many vector spaces are there over Q that are two-dimensional?
R.
R?
Yeah.
R is what?
Like the real number.
The real numbers? I should have clarified. Up to linear isomorphism.
No.
Right, whenever some mathematician has how many, they don't really mean for you to count all cardinality things, because then they're not really seeing any of the structure. This is not a trick question. It's a warm-up question. So 1. So everybody here should put up 1 if they had an undergraduate linear algebra class. Dimension alone determines the isomorphism type of every single vector space. So we know that, okay? Now, you might be surprised to find that very few computer algebra systems today will give you that answer. You can go into, say, Magma, or Sage, or Gap, MATLAB, I bet, too. I've not tried this in MATLAB, so I'll put this one in parentheses, but there's nothing in the theory of MATLAB that would make me think they have done something better than what these really high-tuned algebra packages are doing with it. Let's just stop and describe how we're going to create a vector space, okay? To create a vector space, what do I need to do? What's the data? So, I'll put here, these guys willing to allow many different vector spaces of dimension 2. Okay, I want to try to convince you of that, and if you don't believe me, then afterwards you can sit down with me at a computer and I will type this in and show you that these machines say not isomorphic. They're confident. They're not saying probably not, they're saying not. They found a reason that they're not the same, even though we know that can't be true. Okay? So for those of you who are thinking ahead to what am I bringing up, what we're really going to be talking about here is extensional versus intentional. And this is where the theory of infinity groupoids can really bubble out some ideas that we've had in the backs of our heads. Constance Jones was looking at this back in 1911 when she started writing essays on these problems. This is a really old question. It's 100 years old. And yet we still are barely solving it. Okay? So here's the idea. Let's bubble up to it. How to give a computer a vector space. Any ideas? In fact, let's just, for the sake of having something interesting to see, let's say that we wanted to make a slightly more interesting set of coefficients. Because if it's a little bit larger, I can play more and show you what I mean. So let's say that this is the field that I want to explore. It is Q adjoin I. Okay? Okay, that's often how we actually end up making something like the complex numbers. We don't actually have any real decimals. We just do something like the rationals and throw in an I and call it C. Okay, and it's a reasonable approximation for many goals. Okay, so how would I tell a computer about a vector space over F?
One way is specify a basis.
One way is to specify a basis of whom? Of the vector space. Okay, so let's actually back up. What we're really going to think about is this vector space V. If it's going to be, let's say it's two-dimensional over this F, then maybe behind the covers, I actually think of this as being column vectors, A1, A2, A3, and A4. Where those A's are actually just whatever my computer can handle as rational numbers. Maybe floating points, maybe some kind of fractions. Okay? It stores itself as a list of 4 things and it's happy with life. But that hasn't put the I on it anywhere, right? And how do I get I to work on that?
Make them like the even parts or something like that.
Make them like the even
Make
parts.
the coefficients of
So
the
like I want to
vector
take
parts.
I times this vector here, like 1, 0, 1, 1. Okay?
Yeah.
So what's that going to do?
Flips A4 to -1.
Okay, so we know what it's supposed to do. This is playing the role of being the x-axis, right? So if I multiply by I should rotate the x-axis to the y-axis, so that should become 1. And if this is, pointed out here, then multiplying by I will rotate by 90 degrees. So that'll go to -1, 1. Look at you all understood linear algebra, right? Okay, now that's what it did on one vector. What do I need to do in order to guarantee I've understood I on all vectors? You've already said it, I just want to hear it again. Go ahead.
You write this matrix.
Yeah, so what I want to do is think of I as being transported to a 4x4 matrix. That 4x4 matrix can then pretend to be I. Well, not even pretend, it really plays the role of I. And if we look at it as two-dimensional, it'll be zeros here, 0, 1, -1, 0. 0, 1, -1, 0. And if you take the characteristic polynomial, that little block, you'll see one of those roots is -I and one of the roots is I. So it has the right to play the role of I. Same thing as that business, right? So if I sat there and did this for every number, I'd be here for a while. So what I want to do is minimize the work. I know that everything in Q adjoint I looks like that. So I'd like to be able to do this in a formulaic way. I want to give a matrix for each one of these. And so the matrix I could give would be, say, A times the identity plus B times that. Sounds good? So now, okay, that's how I'm going to give a vector space to this system, right? Now, there was a little bit of choice in here, right? What was some of my choicing?
The way you ordered it.
Yeah, absolutely. I mean, I decided that things would be written like this. I could have just as well as written things like this, right, using -I. I could have used A1 plus I, B1 minus I, and many other bases are appropriate for describing this, and it'll give me some homomorphism to that data set, right? But so here's how systems like this take in a vector space as input. It's just a list of square matrices. Okay? The list of square matrices in this case is VI4, followed by that one there. Okay. If I want to work on a bigger vector space, different list of matrices, right? 3-dimensional vector space might be something like this. I6, followed by 3 blocks, each of them looking like that. All right? Yes?
Just to clarify, you mean I times the identity for all these?
I just mean these two matrices. I didn't catch the question then.
I guess for the linear transformation, you mean I times the identity.
No, I just mean that. I mean the identity 6 matrix, the identity 4 matrix, that
Right, the
these
one with the
matrices
right.
play the role of being that they replace the need for I.
I guess I'm confused because we're taking vector spaces over Q adjoint I. So I'm confused where.
No. I'm taking vector spaces over Q.
Oh.
I'm trying to make them into vector spaces over Q adjoint I. So because the computer doesn't have, you can't sit down and program every way that somebody will do something. They might adjoin the square root of 2. Or something like that, right? So then they'll keep making bigger and bigger things. You can't program a primitive type for every possible thing. So you just have rational numbers. Everything at the ground is rational numbers. Then you start adding in these extra pieces. How do you make that formulaic? You just start doing these, give me the matrices. And if the matrices have the right polynomials, the minimal polynomials, or characteristic polynomials, you're in business. That's the way that we give them. So we just give them as a list of matrices, okay?
James, over on the right, couldn't that be like I2 and then just the upper left block if you're just doing Q adjoin I and not like Q adjoin I?
Could you want me to just put an identity here?
Well, no, that's just like 2 copies of Q adjoin I, right? Because you have like the upper left, the bottom right. But you're saying you just have one element of Q adjoin I goes to that. Couldn't you just do it with 2 by 2s?
It's a 4-dimensional space over Q. I feel like I'm missing everybody here, so like let's sort this out before I plow on further.
Q adjoin I is a 2-dimensional vector space over Q.
We're doing a 2-dimensional over a 2-dimensional.
I was trying to say that I want to make a 2-dimensional vector space. So this is my F,
Yeah.
right? And I want to make F act on 2 copies of F. Because I thought that would be more instructive to see.
Gotcha. Okay.
So what I'm
Okay,
trying
I
to say
see,
is
I see.
how does a number in F turn a vector over here over? So now what I'm saying is underneath the covers, the computer says, well, I want a vector of size 4 then, of floating point numbers, because that's what I can understand. I know how to do that. That's in my machine. And I can give a vector space or a vector of size 2, an array of 2 floating point numbers as my input for Q. And then you have to put on the extra information of what's the addition, what's the multiplication, the scalar multiplication here, we're just defining that. So you add that extra information to it.
Yep. Okay.
Okay?
Yep.
So that's why I'm looking at 4 by 4, but I could have had 6 by 6 or not, or any kind of 2n by 2n page. Each one of these could be a description of this structure. Okay? So now you ask the question, let's ask what does it boil down to say that you have an isomorphism between vector spaces? So what is isomorphism of vector spaces? In this really truly computational way, okay? Okay, so if I had the first vector space Q adjoin I cross V1 into V1, and I had another one, I'll just call it 1V2. Okay, I don't want to change the coefficients, they're left the same. But I'm allowed to put a linear map here, right? And that's the key point. Is I want a linear map and its inverse to exist, right? That's what will make it an isomorphism. So at the end of the day, if I focus on this little f, I'll turn it into a capital F, a big 4 by 4 matrix. So let's see what this is going to do. I'm going to take a little vector v, I'm going to send it over here to v, times an alpha. And it's going to become an alpha times v. Or I could have applied the equal sign to alpha, not changing it at all. I could apply f to it, which is some 4 by 4 matrix, and then multiply them. And I want this to be the same as applying f to this side, like that. Okay, so I've achieved almost nothing, except now I'm prepared to make the coup de grace. Alpha, we've just decided is going to be some 4 by 4 matrix, the image of this thing, right? So I have A corresponding to alpha. I have the matrix F. And here's what I'm hoping will happen. If you look at this running over all these, you really just needed this product to commute. And that's the whole story, right? I just need to have things that commute with the scalar. Okay, invertible matrices that commute with the scalar. All right. Well, now let me try to show you how a computer gets confused. The whole goal is to find an invertible matrix which commutes, an invertible matrix F which commutes with these scalars. Okay? So here I'm going to give you two vector spaces. I'm going to give you two one-dimensional vector spaces. Well, I'm going to pick two nefarious generating sets. Q is generated by the number 2. It's also generated by the number 3, and the number 7, and the number 1, many other things, right? Lots of vectors generate. But this one will assign the matrix A to be 2 times the identity, or whatever dimension of your space is. All right, that's going to be that. This one's going to be 3 times the identity. Okay? Now I'd like to know how we're going to come up with a matrix that's going to commute with a scalar and do anything to it. If you commute with a scalar, guess what you do? You don't change it at all. How am I ever going to turn the 2 into the 3? There is literally no F that'll turn a 2 by 2 matrix, or that'll turn the number 2 into the number 3. It's just not going to happen. And it shouldn't happen, right? Because 2 doesn't go to 3. So what's happened here? Where's the mathematical mistake?
One way to look at it is with AF equals FA, if A is a scalar, it should already commute, so it doesn't matter what the F is.
It's going to matter what the F is. I want to have these be isomorphic, so I do want an F existing. And here, nothing will do that. Right? There's no 1 by 1, all 1 by 1 matrices commute with all 1 by 1 matrices. But this is never going to happen. You're going to have an F that turns a 2 into a 3 here. Okay? Of course, the issue is, why are you trying to compare 2 with 3? Right? The subtlety is in how I ask the question. See, what I did is that I convinced you all that it was enough to just give 2 matrices to tell you how Q adjoin I makes a vector space. And that's not true. Because along with that, I have specified that you must also care about my fixed generating set. I haven't said this is true for any other generating set. I've said that this is a vector space provided you all agree to use my here and now fixed vector space basis generating set. And that's necessary. If I'm going to write down Q adjoin I, I'm going to have to pick some finite thing to write down. So I'm going to have to pick external data to the concept of Q to record it. But that external data is not part of the definitions that mathematicians want to talk about when they want to compare 2 vector spaces. So it doesn't enter into the question of whether 2 things are equal. So when you sit down and actually program on Monday your vector space, and to you, the basis that made sense was 1 and I, but on Tuesday, the basis that made sense was 1 and minus I, you can walk away feeling very confident that you've implemented correctly a vector space for Q adjoin I. What you can't do is compare your results from Tuesday and Monday. And that's a problem. You can see why this starts to add up, why you can't actually trust the computations to talk to each other. And what are you going to do? Just going to have a conference every time you want to agree on a vector space or basis? Like, we're going to have, like, every year we have all the people who are working on this vector space have to go to this conference together, and they will vote on the prescribed basis that we'll all agree to use. No, that's impossible. That's like never going to float, right? So we need a better solution than that. So people have come up with terms that sound fancy to explain what they're doing. In a real sense, all equalities are ramified, meaning that they all assume we've agreed at some level. And the equality is only true up to this agreement, this conference, this mythical conference where we all write down the basis for this particular vector space, right? That conference, of course, never happens. So what we'd like to do for reality check is assume that, well, I don't know that we ever had this conference. Suppose that I did have the truth up to that conference, that where we all agreed that basis. And then I found out the results of the conference that happened next year changed that reality. How would I update my results? So that's the key idea, is be able to update equality. See, what you would find out is that, well, okay, one group said 2, then one group said 3, and then you'd have to say, well, how did I know these were the same vector space? Oh, because there is a way to transfer Q to 3 by multiplying by 3/3, right, or 2/3. That would be changing that map right there from being an equal sign to being an actual transformation, an actual change. But that change could happen before you get started. To adjust those small changes, the choice of basis, before you then go do the isomorphism of the vector spaces by commuting matrices. So that's how I teach the person to then update based on the different conventions. I still have to have that convention happen, but what have I done when I ask for that convention is I've just created a second isomorphism problem. How do you show me that Q by 2 is the same as Q by 3? You have to go and have a conference on why those get to be made the same. Those turn out to need some accommodations. At some level, I put this in a computer. And then I have computers that are built for Intel, computers built for AMD. Some are big endian, some are little endian. Those numbers are not the same number systems. So there has to be a convention. And it's turtles all the way down, right? That's the little phrase of the classic storyline of what's holding up the earth is some turtle. Well, what's holding that turtle up? Another turtle, right? This gets you starting to think, what is the process behind infinity groupoids? So let's go back to this groupoid idea. What was our first example of a groupoid? The one that Amit put on the board at the beginning.
Homotopy? Something with that?
Homotopies, but before that he said one, and then he moved on.
Groups?
Groups are a groupoid, but he didn't use that example, so it's unfair to ask you to remember. Every single category, if you just take the invertible morphisms, will give you a groupoid. Okay? So that was in fact one of the inspirations for categories. There were already things called groupoids out there. People were studying them, and then they needed something more general, not everything being invertible, so they relaxed the groupoid to become what we now know as categories. If you go Google this, you see the story completely backwards. Categories existed before the dawn of time, and everything came from categories. Okay? That's not realistic to reality, but nevertheless, that's the way it is now. So if you already knew what a category was, you could ask for when does that product have an inverse? It's just a multiplication. Multiplications can or can't have inverses. The things that do, we call the core of the category, and they are a groupoid because groupoids just have to have an associative multiplication with inverses whenever defined. So the very first equality is a groupoid. But it's only an equality up to the agreement that we've settled equalities at this mystical conference where we all agreed to use the same generating set. The two groupoid, give me an interpretation of that.
Would it mean that the equalities we agreed on themselves needed some other conference?
Exactly. Exactly. So it was a set of conference agreements. You truncate at that point. You say, okay, at this point, as long as we've made the scalars all agree on these coefficients, and then once you get to the scalars, you say, well, actually, as long as the encoding of the scalars are agreement, then that, and hopefully this thing bottoms out, right? At some point, you hope that, okay, we've made all accommodations for the engineering differences between the two machines. We've made all the accommodations for the different data types for rationals. We've made all the accommodations for the different generators for the rationals. And now we can make the accommodations for the different vector spaces. Okay? And most systems have not gotten that far. And you can see why, because if the sophistication is that you have to be able to update based on later analysis, right? You can imagine that that's a little loop in your program that you've got to sort of say, go fetch the knowledge of how to adjust scalars, and you can see yourself working for a long time to predict all the ways that you'll have to check all these intermediate equalities, right? And I think that's known in the programming circles as impossible, right? You're just not going to predict every way that someone will misuse your code, right? So what we would like to do is build software that doesn't care. Wouldn't it be nice if we just built software that healed itself? Like when somebody makes these changes, we just clickety-clackety saying apply these changes, and it somehow diffuses through all our system. Okay? Anybody know what axiom is trying to pull that off? I know Luke has a book on it. Well, that's the theory, but what's the axiom?
Univalence?
Univalence. So let's tie this all back. So the idea is one groupoid would just say all isomorphisms are created equal. We don't have to worry about patching things up. But that's not realistic. Two isomorphisms, two groupoids, is when, up to some possible rearrangement of some other piece of the story, they're equal. Three homomorphisms, up to 2 layers down, or however many layers down you go. And because we're mathematicians, we don't know when we're going to stop, we just take the limit. So as long as it finishes in the limit, we're fine. We'll call it the infinity groupoid. I don't quite know yet, I'm still trying to figure this out, whether the infinity groupoid that is being used in certain models today is a limit-based or just an unbounded-based. Like, is it that you can always find a larger one, or that you really need the limit ordinal? And in case you've not seen this, please don't be the group of mathematicians who doesn't know there's a difference. Right? I mean, I watched an impressive talk by an impressive person present something that was completely false because he didn't understand induction. If you want to say that something is true on the xy plane, for all the xy plane, and you prove that for any n it's true on this part, you have not proved it for the whole plane. Induction doesn't give you limits. The arguments for limit ordinals are almost always different than they are for any finite ordinal. You would have to make an argument that this covers everything. Have to do the limit. So induction is about reaching every unbounded point, but not reaching the infinity. And if you don't see that difference, you were mistrained. Okay? And even good people make this mistake. All right, so I don't know about which way groupoids are trying to be, but the premise is now, could we make a format for doing math that would translate to programs to solve this problem of turtles all the way down, always redefining our equality, that would be somehow easy to patch up? The univalence axiom says, if ever you find somewhere in the tower something that's an isomorphism, then you can promote that as an equality at that point. That you're allowed to just say, at this point, I don't care about anything below, nothing else is going to matter, I can truncate right there, and now equality moves all the way up the tower, like I zip it all shut. So I can think of this as just putting equals in my program and say, if equals then. And I don't have to go checking intermediate equalities all the way. Now it's clear what you want it to do. You want it to inductively check, where did this truth come from? Where did this truth, until it reaches that bottom point. It's a clear programming strategy. But the point is to not reprogram all our code. The point is to just build code that can do this without having to fetch that knowledge externally ourselves. That the mathematics and the logic of it are consistent. And here's where the path induction is the best path we know. Right now we're trying to say, let's use this path from infinity groupoids to spaces and think about the process of computation as following a path around. And if that path comes back to where I start, that little homotopy loop will be enough to reconstruct this path. That way my program can compile along the path that it lifted to, and I don't have to be the one to drive it through all these different choices of make sure the big endian, little endian are changed, make sure that the left and right are changed, that whatever those little changes are all happening underneath the covers, and I program reliably. That's my motive for learning this area. Doesn't stop you from being interested in topology, but I want you to know that there's a whole different group of people out there that are studying intentional versus extensional for these reasons. Beyond that, I should tell you these words now, and then we'll quit. So these are two forms of logic. If you've ever looked at a set theory book, you probably saw that there was some axiom in there called the axiom of extension, which is declaring once and for all mathematicians that they have to be on one side of logic. This is a little dispute amongst logicians, which was the way to go. So I find it amazing that mathematicians have swallowed a choice like this, because they fight about everything. But somehow, because it's just too inane to look at set theory very deeply, we have somehow just let this go by. But in fact, this would be a place that we could easily find ourselves disagreeing at the lunch table on. So I want you to know that you have a choice in set theory. So the set theory you were taught was extensional by definition. There's an axiom called the extension axiom. But you might want the intentional every now and then in your life. Okay? These are terms that we now use to capture stuff that was going back even to Leibniz. Extensional means to study objects by what things are in the set, what examples exist. Study all examples of a term. So you learn what the term is by pretending you understand all the examples. Intentional is study terms by giving necessary and sufficient properties. Now, as a person who computes a lot in my life, I've discovered I'm never going to have a program that can see all the examples. So almost no program will be extensional. It's not a thing you can do. But I can reason about the properties of the data that will come my way sometime. And I can make predictions about what should happen based on those properties. So I think intentionally quite often. And if you're finding yourself finding it difficult to program a math theorem, chances are often the case that your theorem only argues extensionally. But that if you made it intentional, you would have a well-written program. The theorem would be a program. And that's not just me hoping that's true. That's a theorem. That's called the Curry-Howard isomorphism. Curry-Howard says, if you restrict your intentions, or your logic, to the intentional side of math, then everything is a program. If you want to do extensional stuff, well then some things you just can't think of as programmable. They're undecidable. You can prove that there are actually provably non-programs in this list of things. And that's exciting to know too. Things like there are things you won't ever prove. That's great. That's great mathematics, but it won't help you program. So to the extent that you go out and see yourself using your math, what you want to be looking at is how to exchange extensional for intentional. And category theory so far has been our best hope in this. For 50 years, people have been taking things that looked completely extensional and showing that they're actually intentional when modeled as a category. And I find it's amazing some of the things you can prove. You can prove things completely without any choice of axioms and stuff like that. You don't have to like settle that I'm going to be in ZFC or whatever. Just purely bubble the data together in an intentional way, and all of a sudden you get theorems that you would never expect you could get so cleanly. So that's, I think, what I want to know as I explore. Simplicial sets will get us there. We'll need to back them up with intentional. If we do that in this, I don't know if we'll get to it, but if you want to know the simplicial set is on the extensional side, but when you're ready to move from that to the intentional, you just replace the word simplicial set with cubical. And everything follows in roughly the same way. There's a whole programming language being invented right now called cubical, which is trying to take that stuff and move it down and make it so you can program it today. Does it work? Results are mixed. It's very slow. So they're apparently like trying to build higher homotopy groups, which is kind of one of the hello worlds of this program. But it will, if in principle, if given enough time, it will give you the answer. But it's the enough time part that we need to work on as a community. All right, I'm ready to stop here. Next week, I'm not here, but Amit's going to take over. I think he wants to go through con complexes. If you're interested in being a con complexier, I don't know what the word would be here, you should email him and say, put me to work. Okay? And I think he has things ready for people to read and try to use. And that'll be a very topological take on it, and I don't mind, that's great. But just be mindful that you should know some topology if you're going to take that one on. Any other questions? All right. So that was more of a lecture than less interaction, but we'll come back to that next week when you guys are helping again.